Hello, friends. I hope you are all having a great time. Um, Today we are going to start with section 4 of chapter 4. It's about applications in exponential models. Previously, we have studied exponential functions. What were exponential functions? You're already familiar with. As you know that exponential functions are functions of the type b to the power of x. We said we have got conditions on the b on the base of the exponential function that must be something greater than 0, not equal to 1. We said the x that is considered as the domain of the function takes every value. That means the x that we have got is the set of all real numbers. And then we had, of course, some properties for the exponential functions. Then we came to the logarithmic functions. We said a logarithmic function is a function written like this: logarithm of x with the base of b. Again, that b we have got is something greater than 0, is not equal to 1. That b is the same base that we are using for an exponential function, so that one is also the base of the logarithm. The x here that is considered as the domain of the logarithm takes the values that are positive numbers. So in general, x doesn't take 0 because it will make it undefined, and it does not take negative values. We have studied the derivatives, differentiations of b to the power of x, logarithm of x. We've done some examples on them. Today on that section we are coming to their applications, exponential models. If you have got a model and considered logarithmic and exponential functions in it, how do we deal with them? In general, in that section, sketching the graph of those functions, including logarithm and exponential functions, are required from you, but I'm simplifying it in a general way for you, and I will not ask for sketching those graphs. I'll just ask for increasing, decreasing, critical numbers, local extrema, concavity, and inflection points of those given functions. Okay, so in chapter 3, of course, we have studied those stuff. You're already familiar with those. Today, we are studying those increasing, decreasing functions, concavity, using exponential functions. Okay, we are having, instead of having a polynomial function or a fractional function, we have got an exponential function included in the given function. Let's start with an example. Okay, that's example 4.4.1 in your course material. Given a function f of x that's equal to x squared minus 8 ln of x, it is required from you to find the intervals of increase and decrease. Okay, critical numbers, local extrema, concavity, and inflection points. So instead of saying sketch the graph of the function that is written in the example, I will require you to find the intervals of increase and decrease, critical numbers, local extrema, concavity, and inflection points. As you know, we've studied in chapter 3. For finding increase, decrease, critical numbers, and local extrema, we are using the first derivative of the function. Okay, and for concavity and inflection points, we are using the second derivative of the function. So let's start with the intervals of increase and decrease. We have to find the first derivative of the function, of course. How do you find the first derivative of the function? Simply, we are taking the derivative of this one. Derivative of x squared is 2x minus, I have got the 8 there, and derivative of ln of x, that's equal to 1 over x. Of course, when we are talking about this function, the x that we have got is greater than 0. Why? Because I have got, sorry, I have got the function len of x inside here, and len doesn't take negative values, so I must consider that the domain of that function that I'm working on is something greater than 0. Okay, so here we found the first derivative of the function. We have to find those numbers that makes the first derivative undefined. Okay, as you remember, the first derivative undefined or equal to 0. Okay, so what do we have to find? Those numbers that makes the first derivative undefined or f prime equal to 0. How do you find this one? If you look at that function, do I have any number that makes it undefined? I have it. Of course, 0. Where is it? 0 makes that function undefined. Okay, so x equal to 0 makes the function undefined, but I'm not considering that 0. Why? Because 0 is not in the domain of the function. I have got the domain is something greater than 0. So I'm searching for those numbers that makes the first derivative equal to 0. That means 2x minus 8 1 over x equal to 0. How do I solve that equation? I have to equalize the denominators of this one and that one. So the denominator of this one is 1. I'm simply multiplying numerator and denominator by x. So what will I get? I will get 2x squared minus 8 all over x, that's equal to 0. I have got that one is not equal to 0 because I do not have it in the denominator, in the domain of the function. So simply 2x squared minus 8 is equal to 0. Okay, this is a simple equation. We can solve it. 2x squared is equal to 8. I'm taking this one to the other side. So here I have got x squared is equal to, dividing both sides by 2 to get rid of that 2. Okay, 8 divided by 2 is equal to 4. So x is equal to positive 2 or x is equal to negative 2. But I cannot take negative 2 to consider it inside the function. Why? Because negative 2 is not in the domain of the function. If you look at here, the domain that we have got is greater than 0. So the x's that we find that are less than 0 or equal to 0, we are not considering it. Look, even though here x is equal to 0 is something that makes it undefined, but since it was not in the domain of the function, we didn't take it. We crossed it out. Here again, when we were finding the critical numbers for the function f of x, we got x equal to positive 2 and x is equal to negative 2. Again, we crossed out negative 2. Why? Because we already don't have negative 2 in the domain of the function so that I can consider it. So what is the only critical number that I have got? X equal to 2 is the critical number. Okay? Now, we said when we have got critical numbers, what do we do for finding the increasing and decreasing intervals? We are simply putting it on the real number line. Okay, I'm putting it on the real number line. Of course, the real number line that I have got here starts from 0, okay, and goes to infinity. I don't have negative numbers since the domain of that function doesn't include negative numbers. So what was the critical number that we had? It was 2. So I'm putting 2 on the real number line. Now I have got an interval from 0 to 2. I'm choosing a test number from here. You have to remember how we are doing this procedure. We have studied it in chapter 3 from applications of differentiation. And now I'm taking a test number from 2 to infinity. I will choose 3. Okay, now what shall we do? We have to put that 1 and that 3 into the first derivative of the function. Okay, I am putting that 1 and 3 into the first derivative of the function. What was the first derivative of the function? Let me check it. Here the first derivative of the function. If I put 1 into that function, what will I get? I'll get 2 multiplied by 1 is equal to, or let me write it for you in the other side, okay? F prime is equal to, so that it will be obvious for you, F prime is equal to 2x minus 8 over x, okay? F prime is equal to 2x minus 8 over x. Now we are putting 1 into that function. 2 multiplied by 1 is equal to 2 minus 8 over 1, that's 8. So 2 minus 8 is something negative. Okay, as we said, when we're putting those numbers into the first derivative of the function, we don't care about the value of the function. We just care about the sign, either it is positive or negative. Since we got negative, so we are putting in negative numbers in that interval. What does negative numbers mean? That means that function here is decreasing. Okay. Now we are putting 3 into the function. 2 multiplied to 3 is equal to 6 minus 8 over 3 is something smaller than 6, so I get positive numbers. Since I get positive numbers, look, I didn't calculate the value here, I just know that it is positive numbers, so the function here is increasing. Okay, now we found the critical numbers. Okay, what have we found so far? We found critical numbers, we found the intervals of increase and decrease. What is remained for the application of the first derivative? Local extrema. How do I know that if that point is local maximum or local minimum? We said if it changed sign from left to right, then we are sure that it is a local extrema. To check whether it is maximum or minimum, we are looking at the left and the right of the function, of the critical number. On this side, on the left side, the function is decreasing, it's coming down, and then it is increasing, it goes up. So what is that point? It is local minimum. It is the minimum point of the function. Now, we found all the things that were in the first derivative of the function. I have to find the second derivative of the function to check the concavity of that function. Okay, the second derivative of the function, if you look at it, what is the derivative of 2x? It is 2, okay? Minus, what is the derivative of 8 over x? That's equal to minus 8 over x squared. With that minus, it becomes plus. Why? Because here, when I took the derivative of this one, first I changed this one to 8x to the power of minus 1. So f prime of x is equal to 2x minus 8x to the power of minus 1. Then if I take the derivative of this one, the derivative of 2x is equal to 2. That will be minus 8. What is the derivative of x to the power of minus 1? That will be minus x to the power of minus 2, because the power decreases by 1. So that one becomes 2 minus multiplied to minus becomes positive. 8 over and x to the power of minus 2 comes down, becomes x squared. That's why the second derivative of the function is 2 plus 8 over x squared. Now, if you look at that function, what do we have? We have got we know that the domain of the function, okay, x that we have got is always greater than 0, as we did consider it at the beginning of the function. If I put whatever number into that function, what does it give me? Okay, of course, in the second derivative, we have to find those numbers that makes the second derivative equal to 0 or undefined. I do not have anything here that makes the function undefined, because 0 is the only number and 0 is not in the domain of the function, so I will not consider it. Okay, and if you look at the domain, if you look at that function that we have got, whatever number I'm inputting here gives me a positive number. So f double prime, okay, is always something greater than 0. What does greater than 0 means? That means it is a positive number, okay, positive. Since it's a positive number, what does that mean? That means here is the domain of the function, starts from 0, goes to infinity. That means whatever number I'm choosing here and putting it in the second derivative of the function gives me something positive. What does that mean? That means the function that I have got is always concave up. Does it have any inflection point? it has got no inflection point. Okay, because the function that I have got is always concaved up. It doesn't change concavity. You know that an inflection point is a point where concavity changed. But since the function that I have got here does not change concavity, it is always concaved up. It is always a cup face to up. That means the function has got no inflection point. Okay, so that was an easy example, I think. Let's move to the other example that's given in the material. Okay, but I will simplify it a little bit for you. We have got example 4.4.2. In that example, it's again required from us to find the intervals of increase, decrease, critical numbers, local extrema, concavity, and inflection points. Again, till local extrema, we are using what? The first derivative of the function. Okay, from here to local extrema, we are using the first derivative. For concavity and inflection points, we are using the second derivative. If you keep in mind those stuff, you can do the very little mistakes while you're solving those kinds of questions. Again, the function is given to us, that is given to us in here. It is an exponential function. Okay, so to find those intervals of increase and decrease, we have to first describe the first derivative of the function. So f prime of x is equal to what if you take the derivative of this one? In the previous section, we studied the differentiation of exponential functions, so it would be easy for us to find the derivative of this one. We know that if you have got an exponential function, it is equal to itself, okay, multiplied with the derivative of the power. What is the derivative of that power? That's equal to minus 2x over 2, okay, because the derivative of this one is minus 2x, and we have got the 2 down here. So these two will cancel each other. What is the derivative? That's equal to minus x e to the power of minus x squared over 2. And that is the first derivative of the function. Okay, if you look at that function, we have to find those numbers that makes the first derivative equal to 0 or undefined. Do I have any number that makes this one undefined? No, I don't have it. So I'm simply searching for those numbers that makes the first derivative equal to 0. So that means minus x e to the power of minus x squared over 2 is equal to 0. If you remember when we were studying exponential functions, I know that exponential functions are never 0, okay? This is never 0. Why am I considering that case? Because I have got the multiplication of this one with that one. So either this one is equal to 0 or that one is equal to 0, okay? When we have got a situation like that, we say x equal to 0 or e to the power of minus x squared over 2 is equal to 0. But that one is impossible, okay, because we do not have exponential functions equal to 0. So I will simply get x equal to 0 from that equation. So the only point that I have got, and which is a critical number, okay, that is the critical number. So first we found the critical numbers, is x equal to 0. Now, when I have got x is equal to 0, where do I have to put that x equal to 0? I have to put it on the real number line. Let me draw a line for it. Okay, now I have got 0 here. Again, it divides the real number line into two subintervals, an interval less than 0 and an interval greater than 0. I'm choosing test numbers from here and there again. We have to put those test numbers where? Okay, f prime of minus 1 and f prime of 1. Okay, here minus 1 and here 1. If I put negative 1 into the first derivative of the function, do I get a positive number or a negative number? We know that this one, okay, let me write it somewhere down here, f prime of x is equal to minus x e to the power of minus x squared over 2. That piece, okay, that exponential function, we studied one of its properties was that that function was always greater than 0. We never get 0 from that function and never get negative numbers from that function. So whatever number I put instead of that x, positives, negatives, rationals, irrationals, never gives me 0, okay? Never gives me negative numbers. So that one is always positive, okay? It remains with that part. So I'm inputting that negative 1 into that x. Here, if I put negative 1 instead of x, what do I get? It becomes negative 1. So I will get something positive, okay? When I get something positive, what does that mean? That means whatever I'm inputting here is something positive. This one is positive, that one I get positive. So here the function is increasing, okay? Now I'm putting 1 into that function. This one is positive already. I have got a negative here, and I'm putting 1 instead of x. So negative multiplied to 1, it is negative. Negative multiplied to positive, that will be something negative. So here, whatever number I'm choosing, I will get a negative number. What does that mean? That means the function that I have got is decreasing in that interval. Now, we found the critical numbers. We put it on the real number line. We have found the increasing and decreasing of the intervals. So what is remaining here after increasing, decreasing? I have to check whether that critical number that I have got is local maximum or minimum point. If you look at that function, from the left side it is increasing and from the right side it is decreasing. Okay, here look, it's increasing and here it's decreasing. So what would that point be? Of course, that's the peak, so that will be the local maximum for the function. Now we are done with local extrema, criticals, and the intervals of decrease and increase. What is remained in here? We have to find the concavity and the inflection point of the function that is given to us. Okay, for finding concavity and inflection points, we have to find the second derivative of the function. That means this is the first derivative, minus x e to the power of minus x squared over 2. Now I have to find the second derivative so that I would find the intervals of concavity and the inflection points. How do I find the derivative of this one? That is the multiplication of two functions. So I'm using product rule. So how is product rule? It says first one's derivative, okay, multiplied with the second one, plus second one's derivative multiplied with the first one. What is first one's derivative? It is minus 1 multiplied with the second one without any change. So that one is minus x squared over 2. I have got the positive sign. Then the derivative of e to the power of minus x squared is equal to what? It's equal to minus x squared over 2 multiplied with the power that's equal to minus x, all multiplied with the first function without any change. So that will be minus x. Now simplifying this one, I will get minus e to the power of minus x squared over 2. Minus minus makes it positive, so I have got a positive here. X multiplied with x, that will be x squared e to the power of minus x squared over 2. Let me rearrange this one. Okay, I will just do a rearrangement, putting this one here, x squared e to the power of minus x squared over 2. And I will put this one here, okay? Or you can just leave it like that, doesn't make a difference. Now, if you look at this one, what do I see common? I see this one and that one are common between the two terms. So I will simply take it out to the power of minus x squared over 2. I will take it out. What remains here? X squared is remaining here, and here 1 remains. So that is the second derivative of the function. As I told you previously, when we are finding the derivatives of the functions, simplification was not needed in the first few chapters, but I told you that in the later chapters, we will have differentiation, and we have to simplify them, factorize them, because we will need them. Okay, now again, we are doing the same procedure for the second derivative. We are finding those numbers that makes the second derivative equal to 0 or undefined. If you look at this function, we do not have anything that makes it undefined, so we are simply finding those numbers that makes the second derivative undefined. That means e to the power of minus x squared over 2 multiplied to x squared minus 1, that's equal to 0. So e to the power of minus x squared over 2 is equal to 0, or x squared minus 1 is equal to 0. We said e is never 0, okay? So we are vanishing this part and we are dealing with that part. X squared minus 1 is equal to 0. What does that mean? That means x minus 1, x plus 1 is equal to 0. That's factorization. So x is equal to what? Positive or negative 1. We are not calling this one critical numbers, as you know, but we are putting them on the real number line. So putting those minus 1 and 1 on the real number line, again, subdivides the interval into subintervals. We are choosing test numbers from each interval. As you know, you're familiar with those ones, that's why I'm not explaining further. If I put these ones, if I have got those test numbers, where shall I put them? I have to put them in the second derivative of the function. So I'm finding the second derivative of negative 2, I'm finding the second derivative of 0, and I'm finding the second derivative of 2. The function that we have got here, okay, this one, as we said previously, is always something positive. Okay, it never gives me negative. So if I put negative 2 in here, what will I get? I will get something positive. Okay, now if I put negative 2 in here, what will I get? That will be 4 minus 1, and that's something positive. Positive multiplied to positive makes it positive. What does that mean, positive? That means the function that I have got is concaved up. Okay, now let's do that one. I have got 0. If I put it here again, I get something positive, okay, because I know that e is always positive, so I do not need to calculate it. If I put 0 in here, I will get something negative, because 0 minus 1 is negative, so negative multiplied with positive, that will give me negative values. What does negative values mean? That means the function that I have got is concaved down. Now we are moving to 2. I'm putting that 2 into the second derivative of the function. Again, no need for calculation for this part. It's always positive as it is an exponential function. Then I'm putting 2 into here. That will be 4 minus 1. 4 minus 1 is something positive. So positive makes positive. So whatever number I'm choosing in here, I will get a positive number. And when I get a positive number, that means the function that I have got, and I'm sketching the graph of it, will be something faced up. Now we are searching for the inflection points. These two numbers that we have found, those two numbers, may be they may be inflection point or may not be inflection points. If you look at minus 1, from left to right, okay, we are looking left and right. Since concavity changed from up to down, so we are saying that this is an inflection point. Okay, again, I'm looking at 1. Since concavity changed from left to right, the sign changed, so that one is also an inflection point. So both of the points that we had became inflection points. That's all about that example. Okay, that is page 33. We have done the inflection points, concavity, intervals of increase, decrease, critical numbers, and local extrema. You've studied these ones in chapter 3, and we are doing the same procedures that we were doing in chapter 3, but here instead of having simple functions, simple fractional functions, and simple polynomials, we are having exponential and logarithmic functions in the examples. So it is easy. You just need to know differentiation and chapter 3. Okay, mixing both of those two chapters, you will get section 4. That is a really important section, and I love that section, you know. I love mixing up with the examples and chapters together. Hope you would enjoy watching that video. Hope you would understand whatever I'm explaining. Have a good time, and bye bye.